Counting what you don't want. This may sound like a strange title, so we'll talk about this. This is an interesting concept. Counting is an area of math that sometimes requires out-of-the-box thinking. We have to be a little bit creative. It's all about having the right perspective. And sometimes the straightforward calculation is not the most efficient. Sometimes it's even prohibitively long. So far, a lot of what we've been learning are very straightforward, direct calculations, and those are great in simpler problems. But in slightly harder problems, those would just take too much time. In this video, I'm going to discuss a creative approach that can simplify some of these slightly harder counting problems. So the method I'm going to talk about here involves shifting the focus on what is asked. Suppose we have n total items. Now, if there are no restrictions at all, the total number of orders is n factorial. We can just put those n items in any possible order. Suppose a restriction is given and we want the number of arrangements that meet that restriction. We have already talked about the way to count arrangements obeying many simple restrictions. Now, for a more complex restriction, here's another way to think about it. Every arrangement of the total n factorial, so we have n factorial total orders that we could put the items in, some of those will obey the restriction and some of them won't. And so let's just say we know n factorial is the total number of arrangements. That's the total number disregarding any restrictions. R is the number of arrangements that obey the restriction that we want. And let's just say that Q is the number of arrangements that do not obey that restriction. Well, certainly it's true that R plus Q equals n factorial. In other words, every possible order must be either an order that obeys the restriction that we want or an order that doesn't. Well, we have this simple equation, and we can simply solve this for R. And so this suggests another way of finding R, another way of finding the number of arrangements that obey a particular restriction. This other way means that rather than count the ways that do obey the restriction, we're going to count the ways that don't obey the restriction. We're going to count what we don't want. That's what Q is. And it's always easy to find the total number. The total number, disregarding any restrictions, the total number of orders is n factorial. And so we'll count the ones that we don't want and subtract that from n factorial. That's the basic idea of this. Here's a practice problem. Pause the video and then we'll talk about this. Okay, this is a relatively simple problem. We almost could just write out the solutions here. It's so simple. And I will say that using the direct methods we have learned, we could do this. Counting all the arrangements that meet this restriction, it would be a little more time consuming. It would be a little more difficult. As we're going to see, there's an incredibly efficient method available with this new approach. So first of all, if we just disregard that restriction, what are the total numbers of orders? Total number of orders, 6 factorial, is 720. So if there were no restrictions at all, there would be 720 ways that those 6 kids could sit in order. So we're going to count the arrangements that don't meet this restriction. In other words, we're going to count all the arrangements with Jackie and Marilyn right next to each other. Okay, the ones that do not obey the restriction. And it turns out that's much easier to count. Think about it this way. We could have them right next to each other on the far left, or 1 seat over, or 1 seat over, or 1 seat over, or 1 seat over. And so those 10 ways, those are the 10 places that we could seat Jackie and Marilyn if they were required to be next to each other. With any of these 10 arrangements, the 4 empty seats could be filled by an arrangement of any of the 4 remaining children in any order. So for any one of these, we have 4 factorial, or 24 possibilities for the other children. And so just 10 times 24, 240. That's Q. So there are 240 arrangements that would not be allowed by the restriction. Well, we know the total number is 720. So the ones that are allowed, now we can simply subtract. The allowed restriction should be the total number of orders, 720, minus the 240 that are not allowed. And that gives us 480. And indeed, that's the correct answer. That is the number of arrangements that obey this restriction the number of arrangements in which Jackie and Marilyn are not seated next to each other. Notice that the prompt question contained a restriction involving the word not. That can be a clue that thinking about this alternate way might be true. If they want to know the number of orders in which such and such is not true, it might be easier to count the ways in which it is true. Now that's a general rule, but sometimes when we have to count something that is true, we might need to see that it would be easier to count it when it isn't true. And so again, this is a very funny thing about counting. Counting is a lot about pattern matching. It's a lot about sizing up a problem and getting an intuitive sense for it. There's not a formulaic way to decide what kind of pattern is going to work, but the more you get a sense of counting problems, the more you'll have a sense of this. So I'm going to give you a counting problem now where this is true, where it's going to be easier to count something that isn't true. Here's the practice problem. Pause it, and then we'll talk about it. Okay. Harriet has 6 novels she wants to read, one of which is Emma by Jane Austen. She plans to create a reading list of 4 of these novels for an upcoming trip, and different orders count as different lists. How many reading lists are possible if Emma must be on the list? Okay, so we actually could count this, and it wouldn't be that bad to count it, but let's talk about how to count it in this alternate way. The big insight is that it might be easier to count all the possible reading lists without Emma. So the total number of lists, so we have 6 novels. So for the first novel on the list, I have 6 choices. Second, 5. Third, 4 choices left. And the last, we have 3 choices left. So 6 times 5 times 4 times 3. That's the total number of lists without any restriction. Total number of possible lists of 4 novels in a row. So let's see. 6 times 5 is 30. Then I'm going to do 4 times 30 is 120. And then 3 times 120 is 360. So that's the total number of possible reading lists if there's no restriction at all. Without Emma, we can make an ordered list of the 5 remaining books. So for the first book, I'd have 5 choices. For the second book, I'd have 4 choices, then 3, then 2. 5 times 4 is 20, times 3 is 60, times 2 is 120. And that's the value of Q. That's the value of the restrictions that do not, the orders that do not obey the restriction that we want to obey. So the total number of lists with Emma is going to be the total possible number minus all the lists that are without Emma. So that's going to be 360 minus 120 is 240, and that's the answer. If you see that you're able to do this trick, counting the cases that you don't need, then it will save you time. As you practice, pay attention to which method is employed in the solution. Often, especially in Magoosh problems, we're going to show the solution that is most efficient. And so if we've chosen to follow this, to count the restrictions that do not obey, count the arrangements that do not obey the restriction, then ask yourself, why was that choice made? And that, in fact, is even a great ticket to send in. I don't understand why in the solution they chose to do it this way rather than that way. Excellent questions to ask. If you are asked to count how many arrangements obey a restriction, it may be easier to count the ones that do not and subtract them from the total. So certainly one clue is the word not. Another clue is if there's a restriction that is just focused on a single item, this single item must be included, then it might be easier to count all the ways that that single item is not included.